Okay, so for the solution of problem 4.5, what we want to do in A is to show that x1 and x2 are independent. And as we noted before, using problem 4.4, so using the result from problem 4.4, it suffices to find g1 of x1 and g2 of x2 such that g1 of x1 multiplied by g2 of x2 is equal to the simultaneous density. So we just need to split the density up into one expression only concerning x1 and another expression only concerning x2. And that seems to be pretty straightforward, right? Because, well, this is satisfied. So I can just take in this constant in either g1 or g2. That doesn't really matter. So I'll just put in the whole constant in g1. So that is satisfied if we just let g1 be like this entire humongous constant multiplied by x1 to the alpha minus 1. And then what do we have? E to the minus beta x1. So that seems pretty safe. And then we just let g2 be the rest. So g2 is x2 to the 1 minus alpha, and then multiplied by e to the minus beta x2 to the minus first. So that seems pretty straightforward, right? Because then we have that g1 multiplied by g2 is equal to the simultaneous density. Hence, x1 is and x2 are independent. So that was the solution of the first part. Now we need to try and solve the second part. And the funny thing is that in finding g1 and g2, we have almost solved the second part because we want to find the marginal distributions of x1 and x2. And a really good way to do this is by recognizing the densities. So we know that the density for x1 will certainly involve something with x1 alpha minus 1 and then e to the minus beta x1. And the density for x2 will involve x2 to 1 minus alpha and e to the minus beta x2 inverse. So I've already kind of given away the clue here. What we can do is we can actually notice that x1 is gamma distributed and x2 is inverse gamma distributed. So let us just try now to figure out how they are distributed and with which parameters. So what we know is that we know that x1 and x2 are independent by this point, right? Hence, the simultaneous density is equal to the product of the marginal densities. So the marginal density for x1 is definitely proportional to x1 to the alpha minus 1 multiplied by e to the minus beta x1. And we also know that there's another density that's proportional to this, aka the gamma density. And so just recall that for a stochastic variable that is gamma distributed with parameters alpha and beta, the density is given by beta to the alpha divided by gamma of alpha multiplied by x to the alpha minus 1 multiplied by e to the minus beta x for x greater than 0. So this reminds an awful lot of the thing that we know the density of x1 should be proportional to. So actually already now we can recognize that x1 is gamma distributed, because we know that this is the density of x1 just without the constant. So hence x1 is gamma distributed with parameters alpha and beta with density f1 of x1 equal to, so what we see here is there is indeed a gamma of alpha in play that we can take out, and the reason why we use that one is because we see there is an alpha up here, so the value of the shape parameter is indeed alpha, whereas the value of, no, I'm not sure if this is called the scale parameter. It's either way. It's either scale shape or shape scale. But anyways, the value of the beta here is certainly beta. So and the first parameter certainly has value alpha. So that means that the density of x1 is beta to the alpha divided by gamma of alpha multiplied by x to the alpha minus 1 multiplied by e to the minus beta x. And what we know is also that now we can find the density of f of x2, because that's just the rest, right? Because the simultaneous density is the product of the two marginal densities. So hence x2 has density given as beta to the 2 alpha minus 1 divided by beta to the alpha. So that is beta to the alpha minus 2 divided by gamma of alpha minus 2 multiplied by x2 to the minus alpha minus 1, and then multiplied by e to the minus beta x2 inverse. So I've kind of said the keywords here. This is the gamma distribution, the density for the inverse gamma distribution. So x2 is actually inverse gamma distributed with parameter alpha minus 2 and beta. Yeah, you can look at the density for the inverse gamma distribution in the book and convince yourself of this. So this was a pretty straightforward exercise, actually. And what we can learn from this exercise is, even though we could have found the marginal distributions for x1 and x2 by finding the marginal densities, by integrating with respect to x1 or x2, then definitely the easier route here was just to recognize the densities. So memorize your densities, everyone, and not just the gamma and inverse gamma, but all of your densities that you can find in the book, and put them in your own note collection and remember them for the exam.